The wing part suspected of belonging to that missing Malaysian Airlines jet is now in a lab for
more than a decade after a Boeing 777 carrying 239 souls disappeared into the night sky over Southeast Asia. One retired engineer says he has done what Navy's satellites and $100 million search operations could not. He says he has found MH370, and he says he can prove it using something almost nobody outside a small community of radio hobbyists has ever heard of. Governments call it inconclusive. Families call it hope. Scientists are split down the middle. Today we're breaking down exactly what Richard Godfrey claims to have discovered, how he claims to have found it, and why. Even after everything, the ocean still hasn't given up its answer. Stick around, because this story has more twists than almost anything else in modern aviation history. Malaysia Airlines Flight 370 left Kuala Lumpur just after midnight on March 8, 2014, bound for Beijing with 239 people aboard. Engineers, students, a delegation of Chinese calligraphers, families returning from holiday. The first 38 minutes were unremarkable. Cruising altitude, routine radio checks, nothing that stood out in any log. Then, at 1:19 in the morning, air traffic control in Kuala Lumpur handed the flight off to Vietnamese airspace, and the pilot's response, "Good night, Malaysian 370, became the final transmission anyone would ever receive from the cockpit. 90 seconds later, the transponder went dark. That's the box that broadcasts a plane's identity, altitude, and speed to civilian radar screens. Without it, MH370 became invisible to the systems that were supposed to be watching it every second of every flight. To everyone monitoring Malaysian airspace that night, the aircraft simply stopped existing. Except it hadn't. Malaysia's military radar operates on a different principle than civilian radar. It doesn't need the aircraft to cooperate by broadcasting its identity. It just bounces a pulse off any solid object and measures what comes back. And that system kept tracking something. An unidentified return, doubling back from its planned route toward Beijing, cutting west across the Malaysian peninsula, and then heading out over open water toward the Andaman Sea. Investigators would later conclude, with a high degree of confidence, that this was MH370. The turn wasn't a random drift or an equipment glitch. It looked deliberate. Military radar held onto that signal until roughly 2:22 a.m., when it vanished for good off the coast near Penang. 6 hours after that, humanity had almost nothing. No radar contact, no radio call, no transponder. What we did have, and it would end up being the entire foundation of the search for the next decade, was a piece of equipment nobody had designed for tracking aircraft at all. The plane's satellite data unit, essentially a maintenance modem, kept automatically shaking hands with an Inmarsat satellite parked over the Indian Ocean, roughly once an hour, the way your phone might quietly check in with a cell tower, even when you're not making a call. 7 of those handshakes were logged before the connection stopped completely at 8:19 a.m. Engineers used 2 properties buried in those handshakes: a timing delay that hinted at distance from the satellite, and a frequency shift that hinted at speed and direction, to sketch out a set of enormous arcs circling the globe. One arc swept north across Central Asia. The other swept south into the emptiness of the Indian Ocean. The northern route was dismissed fairly quickly. A Boeing 777 crossing that much heavily radar-monitored airspace undetected strained belief. That left the southern arc, and specifically its final segment, a curve investigators nicknamed the 7th arc, as the best estimate of where the plane went down after running out of fuel. What followed was, by most measures, the most expensive search in aviation history. Naval vessels, contracted survey ships, and eventually autonomous underwater drones combed more than 120,000 square kilometers of seabed, an area roughly the size of the state of Pennsylvania. It took years. It cost well over $150 million. And apart from a scattering of debris that eventually washed ashore thousands of kilometers away on the coast of Reunion Island, Mozambique, Madagascar, Tanzania, and South Africa, the ocean floor gave up nothing. No fuselage, no black box, no answers. For years, the explanation that stuck in the public imagination was simple, almost too simple. The pilot did it. In this version of events, Captain Zahari Ahmad Shah, a 53-year-old veteran with roughly 18,000 flying hours, deliberately depressurized the cabin, incapacitating everyone else on board, then flew the aircraft on autopilot for nearly 7 hours until the fuel tanks ran dry and it descended into the Indian Ocean in what some commentators grimly dubbed a ghost flight. It's a clean narrative. It's also one that a closer look at the physical evidence makes considerably harder to accept without reservation. Start with the satellite data itself, the backbone of the entire search. That final handshake at 8:19 a.m. carried a frequency signature, the burst frequency offset that analysts at Australia's Transport Safety Bureau flagged as unusual. Rather than describing a gentle, controlled descent consistent with a pilot gliding a fuel-starved aircraft down for a survivable ditching, the numbers implied a much steeper, faster drop. Estimates put it as high as 15,000 feet per minute in the final moments. That's not a landing. That's closer to freefall. And a controlled ghost glide scenario doesn't easily explain a nosedive of that magnitude. Then there's the debris. The first confirmed piece, a flaperon recovered off Réunion Island in July 2015, followed eventually by roughly 3 dozen additional fragments recovered along the African coastline. Forensic examination of that flaperon found trailing edge damage consistent with what specialists call flutter, the violent, high-speed vibration a control surface experiences under extreme aerodynamic stress, not the kind of clean separation you'd expect from a slow, deliberate water landing. The flaps themselves were found retracted, meaning the aircraft was still configured for cruising, not for a landing attempt. A separate wing flap fragment recovered in Tanzania showed what investigators described as overload fracturing, again, more consistent with violent impact than a soft touchdown. And then there's the search itself, which was built brick by brick on assumptions. Investigators assumed the satellite arcs were precise. They assumed the fuel burn models were accurate. They assumed the autopilot held a straight course all the way to the 7th arc. Every one of those assumptions was reasonable. None of them were verified. And after years of sonar sweeps, turning up nothing but undersea ridges and empty trenches, it became difficult to avoid the conclusion that the search had simply been looking in the wrong stretch of ocean. By the time the original search was formally suspended in January 2017, families were left with a story full of holes. A search area the size of a small country that had produced nothing, and a growing sense that something fundamental about the official account didn't add up. Into that vacuum stepped a retired British aerospace engineer with, by his own account, an unusually stubborn streak, and an idea that most people in the field considered close to absurd. Richard Godfrey had spent a long career working on some of Europe's most advanced aerospace and defense engineering projects before retirement. He wasn't a hobbyist stumbling into the MH370 mystery by accident. He was an engineer who couldn't let an unsolved technical problem sit unsolved. And a couple of years after the official search went down, he started asking a question that, on its face, sounds like the setup to a joke. Could a missing airliner be tracked not by satellites, not by military radar, but by amateur radio operators broadcasting from spare rooms and garden sheds around the world? The technology he zeroed in on is called WHISPER, pronounced Whisper, short for Weak Signal Propagation Reporter. It's a system built by ham radio enthusiasts to test how far a radio signal can travel by bouncing off the ionosphere, the electrically charged layer of atmosphere roughly 60 to 1,000 kilometers above the Earth's surface. Thousands of amateur stations around the globe send out tiny bursts of radio energy, often less than a single watt, comparable to a nightlight, every couple of minutes, and other stations log weather and how strongly they receive them. None of this was ever built with airplanes in mind. It exists purely so radio hobbyists can compare notes on signal propagation. But Godfrey's insight was this: those signals don't travel through empty space. They travel through the same lower atmosphere that airplanes fly through. And something as large as a Boeing 777, moving at hundreds of kilometers an hour, crossing directly through the path of one of those weak radio signals, can leave a fingerprint on it. A tiny dip in signal strength, a slight shift in frequency, sometimes changes so small they're measured in fractions of a decibel. Individually, each of those blips means almost nothing. It could be solar interference, atmospheric noise, 100 other things. But they're all logged automatically every single time in a free public database called WSParnet, which by the time Godfrey started digging held tens of billions of individual signal reports stretching back years. His theory was straightforward to state and brutally difficult to execute. If MH370 crossed the southern Indian Ocean that night, it must have physically intersected dozens, maybe hundreds, of those invisible signal paths on its way south. If those disturbances could be found and filtered out from the noise, they might trace a route across the ocean with far more precision than the broad satellite arcs ever could. So he built the tools to do it himself because nothing off the shelf existed for this. Over several years, he wrote custom software to sift through the WSParnet archive, filtering out solar storms, background static, and the routine chaos of a constantly shifting ionosphere, looking for anomalies that lined up in both time and location with where MH370 could plausibly have been. Focusing specifically on the night of March 7th into March 8th, 2014, Godfrey identified roughly 130 signal disturbances scattered across the Indian Ocean that couldn't be easily explained away as ordinary noise. When he plotted them in chronological order, they didn't scatter randomly across the map. They lined up into something resembling a flight path. That path began close to where Malaysian military radar had last registered the unidentified aircraft, swept southwest, then curved south, broadly consistent with what investigators had already suspected, but drawn with far tighter resolution than the Inmarsat arcs alone could ever provide. Crucially, the path didn't just trail off into vagueness. It converged on a specific coordinate, roughly 29.1 degrees south, 99.9 degrees east, a patch of deep ocean about 1,500 kilometers west of Perth, Australia, and notably, a stretch of seabed that lay outside every zone the official multinational search had actually combed. For the first time in years, someone had produced a single, specific point on a map, arrived at through an entirely independent method, rather than another vague band of ocean the size of a small country. A striking data pattern is not the same thing as proof, and Godfrey knew it. So he took his findings to a team at the University of Liverpool with direct experience validating exactly this kind of forensic reconstruction. The same group that had contributed to narrowing the search for Air France Flight 447, which went down in the Atlantic in 2009 and took nearly 2 years to locate. 3 tests mattered most. First was a timeline check. Did the whisper anomalies line up chronologically with the known Inmarsat satellite handshakes, or were they scattered randomly through the night? If MH370 caused these disturbances, the timing should be tight. According to Godfrey's analysis, all 130 flag anomalies fell within roughly 4 minutes of a corresponding satellite ping, a level of alignment that's hard to dismiss as coincidence, particularly once other possible explanations, like a different aircraft passing through the same airspace, were ruled out for lack of any other traffic in that stretch of sky that night. Second was resolution. Inmarsat satellite data could only narrow the aircraft's position down to broad arcs hundreds of kilometers wide, useful for a rough estimate, not for pinpointing a search box. But because each whisper signal travels along a specific, known path between 2 fixed radio stations, a disturbance on that path constrains the aircraft's position to a much narrower corridor. Cross-referencing multiple disturbed paths at the same moment in time lets you triangulate a location the way overlapping circles narrow down a point on a map. In Godfrey's case, shrinking the estimated corridor down to roughly 20 kilometers wide in places, an enormous improvement over the satellite-only estimate. Third, and most technically demanding, was ruling out natural causes. The ionosphere, solar activity, and ocean surface conditions can all distort radio signals in ways that might mimic the kind of disturbance a large aircraft would cause. To guard against false positives, Godfrey restricted his analysis to signals in the 14 MHz band, where a Boeing 777 produces a comparatively predictable disruption pattern, and discarded any disturbance weaker than roughly -25 decibels. What survived that filtering The 130 anomalies mentioned earlier clustered tightly along a single corridor across the southern Indian Ocean rather than scattering randomly, which is the pattern you'd expect from a real physical object crossing those signal paths rather than from background noise. When the Liverpool team ran the surviving data through Bayesian probability modeling, the same statistical approach used to help locate Air France 447, they reportedly calculated roughly a 74% probability that MH370's wreckage lies within a relatively small patch of ocean centered on Godfrey's coordinates. Not certainty, but considerably more than a hunch, and enough to make experienced investigators who had watched a decade of speculative theories come and go sit up and pay attention. No claim this bold survives without scrutiny, and it shouldn't. 3 objections came fastest and hit hardest. The first, Whisper was never designed to track aircraft, so how can anyone trust it for something this consequential? That's true as far as it goes, but repurposing a tool beyond its original intent is hardly unprecedented in science. X-rays were discovered almost by accident during unrelated experiments with cathode rays in the 1890s. Penicillin came from a contaminated petri dish, not a deliberate search for antibiotics. GPS began as a military targeting system decades before it started giving turn-by-turn directions to the nearest coffee shop. The underlying physics of how radio waves bend and scatter when something massive crosses their path is well-established, decades-old science. Even Joe Taylor, the Nobel laureate who helped develop Whisper, has acknowledged that aircraft can measurably disturb these signals, while remaining more cautious about how precisely you can pin down a location from that disturbance alone. To address that caution directly, Godfrey's team didn't stop at retrospective analysis. In late 2024, they chartered an actual Boeing 777 and flew it along a corridor over the Indian Ocean, closely matching the suspected MH370 route, while Whisper stations worldwide log data in real time. The disturbances that showed up lined up with the aircraft's actual GPS track position with striking precision, not somewhere in the vicinity, but tracking almost to the minute. That live test is arguably the strongest single piece of evidence that the method works in principle, independent of whatever happened to MH370 specifically. The second objection is more personal. Critics point out that Godfrey's estimated crash site has moved over time, from an initial estimate near 33 degrees south to 34 degrees, and eventually settling around 29 degrees south. Doesn't a moving target undermine confidence in the method? It's a fair question, but shifting an estimate as better data becomes available isn't a red flag in serious research. It's how research is supposed to work. Copernicus's early heliocentric model wasn't fully accurate either. It took generations of refinement by later astronomers to tighten it into something reliable. What matters more than the fact that Godfrey's estimate moved is that it stopped moving. His figure has held steady around 29 degrees south for well over a year now. As more Whisper data has come online and his filtering methods have matured, a sign that the estimate has converged rather than simply drifted around at random. The third objection is the hardest to answer because it's simply true. Nobody has physically found wreckage at that location. Until a piece of the airframe or a black box is physically recovered, this remains a theory, however well supported. But independent physical evidence does point in a compatible direction. Oceanographers at Germany's GMR Helmholtz Center for Ocean Research ran large-scale drift simulations, essentially modeling how debris would have moved through Indian Ocean currents over months and years, then running those simulations in reverse from the actual locations where confirmed MH370 fragments washed ashore in Réunion, Mozambique, Madagascar, and elsewhere. The majority of those reverse drift paths converged on an origin area within roughly 100 kilometers of Godfrey's coordinates, a genuinely independent line of evidence, developed with entirely different data and methods, landing in roughly the same patch of ocean. Here's where the story gets complicated in a way most retellings gloss over, and where it's important to be honest rather than triumphant. Malaysia did act on this data. In early 2025, the Malaysian government signed a new no-find, no-fee agreement with Ocean Infinity, the marine robotics company behind the 2018 search, to investigate a roughly 15,000 square kilometer zone in the southern Indian Ocean centered on the whispered-arrived hotspot. Ocean Infinity brought its most advanced fleet yet, including autonomous underwater vehicles capable of diving to 6,000 meters and mapping the seabed with sonar precise enough to identify wreckage-sized objects. That search happened. It ran in two phases, a short window in late March 2025 and a longer 55-day push from late December 2025 into late January 2026, wrapping up on January 23, 2026. After covering more than 7,500 additional square kilometers of seabed on top of the roughly 140,000 square kilometers Ocean Infinity has now mapped across all its missions since 2018. And as of that date, it ended without locating the aircraft. Ocean Infinity's CEO, Oliver Plunkett, was candid about the disappointment, saying the team had thrown every available piece of information and every available technology at the problem and still come up empty, while acknowledging just how genuinely difficult the scale of the challenge remains, both geographically and technically. That's not the end of the story, though. Roughly 7,400 square kilometers of the originally planned search zone were left uncovered when Ocean Infinity's vessel had to be temporarily redeployed to other commercial contracts. In late June 2026, Malaysia's government approved a one-year extension of the search agreement, pushing the deadline out to June 2027, with Ocean Infinity expected to return to the search zone between November 2026 and April 2027. During the calmer sea conditions of the Southern Hemisphere summer. Malaysia's Transport Minister, Anthony Loke, has been explicit that this extension reflects the government's continued commitment to giving victims' families some form of closure, even after so many false starts. So where does that leave Richard Godfrey's theory? It's neither vindicated nor debunked. The most recent search phase covered ground within and around his proposed hotspot and didn't find wreckage there either, which is a real, meaningful setback for the whisper hypothesis, not a footnote to wave away. At the same time, roughly a third of the originally planned search box remains uncharted, and Ocean Infinity itself has said its commitment to the search hasn't ended, only paused for logistical and seasonal reasons. Whether the remaining unsearched stretch of seabed holds the answer, or whether Godfrey's coordinates turn out to be another well-argued dead end in a mystery that has already produced plenty of them, is something nobody can honestly claim to know yet. It's worth stepping back and asking why any of this matters beyond morbid curiosity. 12 years on, this isn't just an unsolved puzzle. It's an open wound for the families of 239 people who still don't have a body to bury or a definitive account of what happened to someone they loved. Lee Uryo, whose son was aboard MH370, put it about as plainly as anyone could. What does it even mean to say contact was lost if there's still no way to reconnect? Voice 370, the advocacy group representing victims' families, has spent years pushing governments and companies alike to keep searching rather than let the case quietly fade from public attention, and their persistence is a large part of why this latest extension happened at all. There's also a genuine scientific legacy here regardless of how the search ultimately resolves. Godfrey's whisper-based passive radar technique has already been used to reconstruct the flight paths of dozens of other aircraft as a way of validating the method, and it represents a real, tested addition to the toolkit available for locating missing aircraft and vessels in the future, built, almost improbably, out of a hobbyist radio system nobody originally designed for anything remotely like this. What happens next depends on weather windows, funding, and whether Ocean Infinity's vessels can be freed up from other commercial work in time for the November 2026 season. If the remaining 7,400 square kilometers get searched and still turn up nothing, that will be a serious blow to the whisper hypothesis, and the mystery will likely deepen rather than resolve. If, on the other hand, something finally surfaces in that final unsearched stretch, it would represent one of the more remarkable vindications of citizen science ingenuity in recent memory. A retired engineer, a network of radio hobbyists, and a database built for an entirely different purpose succeeding where satellites, navies, and hundreds of millions of dollars in dedicated search technology could not. Either way, the story of MH370 isn't over. The search resumes, weather permitting, later this year. And for the families who have waited 12 years for an answer, that alone is more than they've had in a long time. Thanks for watching. If this story kept you hooked, let us know your own theory on where MH370 might actually be. And stick around because there's another deep dive queued up next that you won't want to miss.